Alright, so good morning guys, this is Stereo Police and I am back with another video, this time returning to THD. This one's going to be a much better video than than part 2 I think I just made, and the reason is I have a new scope. I got fed up with my previous oscilloscope. It was basically a cheap, well, it was a cheap Chinese knockoff basically. Years ago I used this guy here, the Beckman Industrial, and it took a long time before I bought a digital storage scope with an FFT analyzer, which is down there. And I didn't have a big budget. So got some unknown Chinese brand, and the instruction manual that came with it was, you know, very typical of that kind of, you know, Chinese knockoffs. It was horrible. And not only was now it was it seemed fairly accurate, except when it came to the FFT, the fast Fourier transform. It was very limited in that sense, and I won't even get into the details. But as I started making some THD measurements with the Keithley, and I was kind of going back and forth and analyzing the spectrum, which I don't have displayed right now, but analyzing the spectrum of an output signal versus the THD reading. The two weren't quite meshing well enough for me, and I came to realize two things. Long story short, one, the scope wasn't doing a very good job at resolving frequencies or amplitude in the frequency domain, but also I was doing something wrong, in part because the instruction manual was very much lacking. And the instruction manual that came with the Tektronix here, which is my THB 1052, I'm sorry, my TBS 1052B, the instruction manual was much better, and I was really able to figure things out. To use FFT analysis on a scope such as this one, it really helps you really have to know the underlying theory of sampling, and you really have to have a good instruction manual to if you've never done it before, to really explain things to you, what you need to do and why you need to do it. There isn't kind of an automatic mode on here that works pretty good, and I'm going to make a video one day about this oscilloscope specifically, so I won't get into the details now, but I've learned to use it. I've spent probably 6 or 7 hours yesterday toying around with this thing, running some numbers and figuring it out, and I'm very confident in the results now. In fact, what I'm going to show you today, hopefully, if I have the time, is we're going to do a THD calculation based on the frequency spectrum as displayed on the scope, and compare it to what the Keithley says. The Keithley can certainly be trusted. I trust that completely, and we're going to see if we can come up with roughly the same numbers, just based on the FFT display here. But just as a recap, last time we talked about, well, right now I've got a 1 kilohertz tone being generated and input into this really crappy amplifier that came, I think I showed you this before, but it came out of this box right here. It's just a little mini audio amplifier, not intended to be anything substantial, and I have it actually running through a speaker, which I have covered up because this 1 kilohertz tone is annoying as heck, and I'm going to be turning it up in a minute. So I've got a little speaker here, and I'm monitoring the input and output signals, and the input signal you see there as the blue trace, and the output across the speaker is what you see in yellow. You can certainly see there's quite a phase shift there from input to output, roughly 90 degrees actually, and but that's here nor there. So what we talked about last time is, well, actually, of the of the 4 ways of measuring THD that I'm going to discuss, the first one was simply listening. And we all know when you turn up a cheap radio too loud, you know what distortion sounds like. You know when you reach that point. Everyone knows what it sounds like. It sounds harsh. And you know, you can definitely tell when you reach that point. And just as a demonstration, and I did this before, I'll do it again with a sine wave, with our 1K sine wave. As I turn this up, I might have to adjust a couple things here. So we still have a nice sine wave on the output. We still have a nice sine wave on the output. Input is in blue, output's in yellow. Okay, now I'm going to turn up the gain on the amplifier. It's got a little potentiometer. Okay, that's very sensitive. Okay, we can hear, unfortunately my air conditioner is running now, but we can hear a pure tone. And then as soon as it starts to clip, you can hear the overtones. Okay, we're down to a pure, fairly pure tone. Overtones. Excuse me. So even without an oscilloscope or a voltmeter, or if you just had a signal generator of some kind and you cranked it way up, you can tell. If I wanted to measure, for example, what the peak, roughly what the peak output power is, I could turn it up to the point where I'd start to hear those overtones, turn it back down to where I really can't hear them anymore, and then I could measure the voltage across the load and run the power calculation, V squared over R, for example. So that's one way. Now the second way, we could measure THD without this sophisticated Keithley here, is with an oscilloscope that has fast Fourier transform capabilities. The third way is with an old-fashioned, such as this Heathkit here, THD meter, which is a lot of manual work. I'm not going to go into detail about that because there are some other videos on YouTube that discuss how to use that thing. And then the best way is with a THD analyzer, and a high quality one at that, such as the Keithley 2015 THD multimeter. But for now, what I'm going to do is I'm going to, so I don't have to hear this tone, I'm going to switch my load to an 8 ohm dummy load, so we don't have to hear anything. And then we'll go ahead, there's my dummy load. That's one of them actually. These are two 8 ohms, 8 ohm 100 watt wire wound resistors. If FYI, if I ever want to determine for a higher power amplifier, do a stress test on it where I take it up to 3/4 or more of its peak power and leave it there and see if any thermal protection circuitry kicks in, then I use this guy right here. And I've got 4 and 8 ohm taps, and each of these is a one. This is my bank for these are 4 ohm resistors, and then this is my bank for 8 ohms. So I have the capability of these are 100 watts each, so 400 watts. And then what if I reach that peak, then I have a little fan, a little tiny desktop fan that I turn on and blow over top of this to get rid of the heat. So I don't really need this right now. I hardly ever need it, but I have it. So hold on, I'll get these. I'll get a dummy load hooked up, and we'll calculate THD directly from an FFT and compare it to the Keithley. Okay, so I'm all set up here. I am set up to take some distortion measurements, or I should say derive them or calculate them directly from an FFT. Measuring the distortion characteristics of this little crummy little amp here, driving an 8 ohm dummy load. I also, the signal source is audio oscillator at 1 kilohertz, and I have the Keithley THD hooked up right now. I've got a fairly clean waveform that's close to the top of its range, so that I can get into clipping in a second. As you can see, the THD is 0.4%. It's about as good as it gets for this amp, I think. So let's drive the amp into a little bit of clipping. You can start to see the peaks get a slope on it, and let's see what that 3.9, 4%. So let's see if we can. Okay, we got a 4% Keithley. Let's see if we can. There we go. Let's see if we can calculate this from the FFT. So first, I'm going to do an auto set. I don't want that channel on. That is the blue trace is the input. I'm just going to get rid of that altogether. Okay, so I did an auto set. I'm going to hit FFT. There's two ways to get to access the FFT menu. It's a little easier from auto set because it pre-calculates a good sampling rate for you. Okay, so got a sampling rate of 25 kilosamples per second, which means I can accurately measure out to about 12 kilohertz without aliasing. And I know that I have a 1 kilohertz fundamental, and I have 5 predominant harmonics, and the last harmonic, this would be 1, 2, 3, 4, 5, 6, and 7 kilohertz. 7, 7 is 14. So I should be fine. I don't see any evidence of aliasing happening right now. So we are fine. Now, the first step is to measure. Now we're going to basically do here from the FFT, and I'm going to go ahead and hit stop and take a screenshot here so we can work with this with the cursor. Now where I took the screenshot, we have an FFT of 4.0. Okay, so let's see if we can derive that 4.0. So just going through a couple of motions here. As I said, this stuff down at the bottom is noise. These are harmonics. This might be a little bit of aliasing right here. But these are low enough in level. I'm going to try to calculate it from the predominant harmonics, which is V2, 3, 4, 5. There's nothing, and 7. And it doesn't matter where the frequencies are, although just FYI, I'll put a cursor on the frequency. Let me turn. I have a lot of glare from this light. I'll turn that backlight off so you can see. I'll put a cursor on the frequency, and you can see I'm moving. This is cursor 1, and I'm moving it. I'm going to move that to the fundamental, and cursor 1 is now at 1 kilohertz. And then let me go to cursor 2, and you can see cursor 2 down there moving around. You can see we have a harmonic at roughly 2K, another one at 3. See, so we know that those are the harmonics that are being introduced because of the distortion. So now let's get magnitudes. So I'm going to change the cursor from frequency to magnitude, and these the magnitudes are given in decibels relative to 1 volt. reference to 1 volt. So we can easily convert that to flat out voltage, which is what we're going to need. So what I've come up with is we're going to take a series of measurements. Okay, V1 is the fundamental. It looks like a function, but it's not fundamental. V2, V3, V4, V5, and V6. These are the harmonics. And I'm going to read them in dB off the scope and then convert them to RMS, so that what we can do is calculate our THD. Okay, V2 squared plus square root divided by V1, which is the fundamental, all in RMS. So that's the goal here. It might be tedious, you might want to skip ahead, but I'm going to do this live to see if we come out with a decent answer. So, cursor 1 is at 4.23 dBs. 4.23. Now I'm going to lower the cursor to measure V2. And it's at negative 40. No, sorry, negative 37. Negative just means that it's less than 1 volt. Okay, I'm on V3. Negative 26. V4. Cursor 1, negative 40. V5, negative 31. There is no V6, so I'm going to go right to V7. Okay, you see, V6 is missing. There is a predominant V7, so let's do that. Negative 36. And there are some lesser harmonics. Some of this looks like a little bit of aliasing, but the harmonics slowly fade away, and I think we can get an accurate reading based on these harmonics alone. If we're a little bit off, it's because I didn't go to the nth lower, I didn't grab these, but these are so low. Remember, this is a decibel scale. So the low voltages are accentuated, the high voltages are collapsed, so that you can see everything on one screen. These are very, very low. I seriously doubt, and there's that. I think that looks like a little bit of aliasing there because of my sample rate. I could go a little higher in my sampling rate, but I don't think it's necessary in this case. So we have our dBs. Now the next question is, how do we convert dBs to flat out volts, RMS? Okay, one way is to use a dB calculator online. You enter your gain or loss in decibels. Have to use the positive or negative. I mean, you have to be cognizant of polarity. It makes a huge difference, and it will give you the voltage RMS. This goes the other way. Just to show you how to do it manually, if you wanted to, and I'll just pick a number of dBs that's easy to work with. Let's say you have 20 dBs that you've. That's a 20, yes. dBs that you read off your scope. Well, we know how to calculate it. No matter what the number here is that you read, it equals 20 log base 10 of the voltage that we're looking for. I'm going to call that Vx. In this case, I already know the reference because it's the way the scope is set up is 1 volt RMS. Now anything divided by 1 is 1, so we don't care about that. We know that our answer is going to be in voltage RMS, which is what we want, right? So in this case I picked 20 because I can do the math in my head, okay? So we bring the 20 over, 20 over 20 equals log Vx, right? This becomes 1. 1 equals log Vx. Now we have to get rid of the log, and the way you do that is with an anti-log, which basically means I raise both to 10. This is log base 10. Okay, so 10 to the 1 equals Vx, right? And 10 to the 1 is 10. So Vx equals 10 volts. We could do the exact same thing with all of these dB numbers, but that's a bore. Let's use the dB calculator. The fundamental is 4.23 dB positive. Trying to do this holding the camcorder in my left hand, it's kind of awkward. What did I say? 4.23. Okay, and we hit calculate, and that's 1.63. By the way, there is a way to do this calculation directly from dBs, but I'm not going to get into that. Not even going to go there right now. I prefer to work with voltage. So the next is negative 39. Negative means whatever voltage this is going to be less than 1 volt. See, that's higher than 1 volt, positive dBs. This will be less than 1 volt. Quite a bit less, because look, it's 39 dBs. I mean, that's significantly less. So let's run the number. We have to put a negative in there. Did I say 39? I did. And we get 0.011 volts. The next one is negative 26. .05 volts. I'm going to bore you with this because I'm going to do the whole damn thing. Negative 40. .01 volts. Negative 31. .028. 0.028, and negative 36. We haven't done that one yet. Negative 36. We're almost there. 0.016. So now we just have to crunch that equation right there. So I will get another sheet here, and I'm going to enter those numbers. THD equals, and square root of the sum of the squares of. Now again, these are the harmonics, that's the fundamental, so I'm going to start right here with 0.011. 0.011 squared plus 0.05 squared. My 5s look like S's, I know. Plus 0.01 squared plus 0.028 squared plus 0.016 squared, all over the voltage of the fundamental, which is 1.63. Okay, where's my calculator? Oh, by the way, this is all times 100 to get a percentage. Otherwise, you'll get a decimal. Same thing, but you gotta know what you're looking at. We want a percentage. So, calculator. Try to do this all in one fell swoop. 0.011 squared plus 0.05 squared plus 0.01 squared plus 0.028 squared, finally plus 0.016 squared. The whole thing equals, and we take the square root, then we divide by the fundamental, 1.63. Look at that, we're gonna be pretty close. Times 100, and we get 3.76%. And because of my precision here, I'm just going to say 3.8% THD. What did we ask? What did the Keithley tell us? Told us 4%. So, pretty close, you know. I mean, that's close enough. So that, my friends, is how you can measure THD if you have a scope that performs math and specifically performs fast Fourier transform. But you have to. This is beyond the scope of today's video, but you really have to know how to use the FFT on your scope. There are a couple of things that can really screw you up. One of them is aliasing. Let me start out with the two things that can really screw you up, and then we'll go on to looking at these other two instruments here. Okay, I was on a stop, I paused, so let's get back to real time here, and here's our signal. Okay, one thing that can really screw you up is the way this machine works. There's our ugly waveform there. Is that the machine this particular machine samples 2048, I believe, sample points within 8 grid spacings. 1, 2, 3, 4, 5, 6, 7, 8. Within these 8, it'll sample because of the internal memory. It'll sample 2048. I believe I got that right. Sample points, and that's going to stay the same. Let me get to that in a minute. Let me start out with amplitude. So with amplitude, it's also going to sample whatever's on the screen here. It's like taking a snapshot of it, right? And so if you were to adjust the vertical so that you clip the waveform on the screen, that clipping that you've induced will also reflect itself. Let me make it really gross here. Will also reflect itself in the Fourier spectrum, and the harmonics that were added artificially by your clipping on the screen will show up in the fast Fourier. And you don't want that. There's a ton of harmonics there. You don't want that. So you want to make sure that the signal or the waveform you're looking at is not beyond the limits of the screen. Otherwise you'll be looking at harmonics that you made on the scope and not harmonics that were made by the device itself under test. And the second thing is sampling rate. When you do an FFT, I'm going to do an auto set right here, and the auto set will bring up an FFT for me. When you do an FFC, the scope is going to tell you the sampling rate right here, 25 kilosamples per second. Keeping in mind that you have to sample. What is it? It's been a while. The Nyquist frequency, I guess, NF, I think that's how it is, has to be twice the highest frequency that you intend to sample. Really, that should be, highest twice. That's 2 there, not, okay, 2. In order to accurately sample without aliasing. Aliasing is all kinds of aliased or ghost or improperly present frequencies will show up where you don't want them to, and you can notice them because they're not going to be at the harmonics that you expect. Okay, so if this sampling rate is 25 kilosamples a second, then that means the best I can do without aliasing is half of that. So the highest frequency I'll be looking at is what? 12.5 kilohertz. Now, what I need to take into consideration is what do I expect to be getting out of this? Now, this is I know I'm inputting 1K, and I know that from experience that these harmonics rapidly decay, and typically you only get, unless it's grossly distorted and you're turning it into a square wave. In audio, you're going to get 3, 4, 5, 6. We had 7 a second ago. Well, this is 1K, 2, 3, 4, 5, 6, 7K. Right? So, if I'm going to sample 7K without aliasing, then I need at least 14K kilosamples a second, and I've got 25, so I'm fine. The same kind of you have to be cognizant of that, because that's as you increase the frequency of the fundamental, you need a higher sampling rate, and you can adjust that on the scope. Now, that's the extent I'm going to get into that today. But let me show you what happens if we were to artificially increase the amplitude on the display beyond its capabilities. Okay, all I got to do is rotate that to the right and to the left, and I'm going to do that in the frequency domain. So here I go, rotate it to the right. Look what happened. I'm going to do it again. And let me bring that up. There's going to be, I don't know if you can tell from here, there's going to be look at that, all kinds of additional harmonics that pop up that weren't there before. And those are artificial. Let me bring her back down. That was probably not a good demonstration. So where we are now is with the waveform fitting. Let me here's what the waveform fitting. There's our FFT. Okay, take a look at that and memorize that thing. Now if I go, if I take this off the screen, it's going to introduce harmonics, and look at that. Nothing has changed with respect to the signals that I'm inputting here. What has changed is I'm off the screen, and so I've artificially introduced harmonics by virtue of how this thing samples. Let me go back. See, I'm off the screen. Let me bring it back down to where I'm on the screen, do the FFT again, and that's normal. Now I'm going to rotate the knob while staying right here. See, that's, can't do that. It makes everything bigger, and I got to move it around with the cursor. So let me do that one more time. This is, everything's on the screen. Rotate once to the right, I'm off the screen, back on the screen. Okay. Normal FFT, off the screen. All these harmonics just added up, and those harmonics are because essentially it's analyzing that. It's as if this waveform goes up, clips, comes down, clips, hard. That's what the scope thinks is going on. So anyway, you get the idea. You've got to keep, because this machine takes a snapshot of what's on the screen essentially and samples it, you've got to keep everything on the screen that you want to have sampled. From magnitude, also in the magnitude direction, it's got to fit, and in the frequency direction, you have to adjust the frequency to ensure that you have enough sampling points to at least get two samples for the, at least two samples for the highest wavelength present that you expect. Too much information, right? But anyway, we calculated THD directly from the scope. It meshed pretty well with the Keithley. Okay, the Keithley said 4%. We calculated 3.8% directly from the harmonics. We probably could have gotten a little more accurate if we hang on a second. Let's make this point here. I'm going to hit auto set. I hit auto set because it's instead of going to this FFT, the FFT automatically sets what it thinks is an acceptable sampling rate, and it usually is pretty good. So, okay. So I probably could have gotten a little more accurate if, I mean, here's the harmonics we use, 2, 3, 4, 5, and 7. I could have estimated, hang on, I could have estimated this missing harmonic that I didn't use, and maybe that one there. 1, 2, 2, 3, 4, 5. I could have estimated 6 and maybe 8. And that might have gotten us a little closer, because that would have added some THD. That might have gotten us a little closer to the 4. But the measurement error here is twofold. Number one, I didn't use all the harmonics, and number two, you know, just placing the cursor where I think the peaks are is not exactly precise. I could have zoomed in and got it, you know, more precise, or actually captured the data from the scope itself, but I don't want to do that. Don't need to do it. That's close enough. Okay. Now, we talked about listening just simply listening to tones, and you can tell when THD kicks in. We talked about how to calculate it directly from FFT, digital storage scope. Two ways of doing it are with dedicated machines that actually directly calculate THD. One of them is that Heathkit right there. I'm going to avoid a demonstration of that because it takes forever to use. It's got to warm up. There's a bunch of factors, and it's kind of annoying. And I never want to use it again because I have the Keithley. But there are videos on the web about this very machine, and if you're interested in it, this is a Heathkit Harmonic Distortion Analyzer, model IM5258. There's different variations of these, and there are people on the web on YouTube that show how to use them and how they're used. And in essence, what that machine does manually through the meter and setting some ranges, but manually what that does is in essence what we did right here. What that machine does is it finds the fundamental with help from you. It finds the fundamental, it sets a filter to the fundamental, measures the voltage, and then it notches it out. It gets rid of it, and it measures everything else that's left over, and then it performs in essence this calculation as a percentage of everything left over to everything left over squared, summed, square root, etc. I'm talking the dBs, which is actually voltage. Everything left over divided by the fundamental times 100, and it'll show up on that meter right there. There's a portion on this meter, and I can't read it because of my glasses, but that's for percentage distortion. It has to be, again, these dials have to be adjusted to, it's kind of, I haven't used it in a while, and I probably couldn't even do it right now without refreshing myself because I haven't used it in a while. So that's another way to do it, and the final, ultimate way is to get a damn good THD analyzer, which is this Keithley. The way this works, it's super simple. I'll just go through a setup procedure. Let me get a waveform back here. Okay, we know this is distorted because you can just look at it. Right now we're at 5% THD. Let me bring this down to a nice clean waveform. There we go. And now see we're now at 0.39. So the way this works is, knowing what we know about THD, is I'm going to start out with measuring AC volts and then switch over from there. Okay, so now for THD we simply, and this meter does a lot of things that I'm not even familiar with yet because it's a long owner's manual and operator's manual. I haven't gone through it yet, but for THD you can see the little THD right there, and you need to hit shift THD, and you should go through a setup. So there's a setup button right there, and there's only a couple of menus, and I have options here of THD, oopsie daisy, let me start that over again, THD type, and I have options for THD alone, THD plus noise, Sinad. That's for specific fields. Is that for power lines, things like that? I'm not sure. I never worked in that area, but I don't need it. And I just want THD. I don't want THD plus noise. Although that is very useful sometimes. Okay, so I just want THD. The next I hit enter and auto. Now there's different ways of this machine ascertaining the fundamental frequency. You can actually set the frequency manually. You can there's let's see what the options are. Auto is what you want to use though in this case, because it automatically tracks the fundamental. If it drifts a little bit, it tracks it, maintains a good THD measurement even as frequencies drift a little bit. But the options are auto, set. I could actually set it to 1 kilohertz, but then if my source drifts a little bit, then my THD won't track it here and it'll be a little off. You can have it acquire it one time and then go with that one acquisition, but auto tracks drifts, so I want to use that. The next thing is the upper harmonic, and I can actually set how many harmonics. You saw we just went to 7, I think. I can actually set how many harmonics, what my limit is, and I stick with 6. If I knew there's going to be a ton of harmonics there, then I can raise that, but 6 is perfectly fine. You reach a point of diminishing returns after that, typically in audio applications. Not always, but mostly. Okay. And the next one is in the units. We can get percentage or decibels. I'm going to stick with percentage. And there are various shaping filters that can be used, and that's a whole other topic. Shaping filters. I'm not going to get into that in detail, but when you capture, remember I told you in the middle of the grid there's a window of 4 plus 4, and whatever waveform is in there is going to get sampled 28, 40, 24, what did I say? 20, 48 times, based on whatever time scale you have there, and in magnitude it'll sample in this direction from the top to the bottom of the screen, right? Well, what happens is usually if I just sample everything in this square right here, there's no filtering. But what happens is the way the THD works mathematically is it wants to see a continuous signal, but we're clipping a signal on the left and right, and then it sort of assumes that the signal is going to end where it begins and so forth. But what if you were to transpose this signal over to here and it began right there? There'd be this discontinuity right there, and that would add a bunch of higher harmonics. So in order to reduce that possibility, what you can do is take this waveform and put a window on it like that, so that in the middle of the waveform we have, the amplitudes are accurate, but as we slope down, they go towards 0, and that ensures the beginning and the end start and end at the same place to avoid those upper harmonics. And what that does is it makes things more accurate frequency-wise, but you can see it snubs the amplitude towards the edges, so you get a little bit of amplitude distortion. So it depends on what trade-offs you want. Do you want accurate, good frequency resolution and accuracy, or do you want amplitude? And there are different windows that help you along those ways. Right now I'm not using a window at all, and everything is fine because I'm not worried about the frequencies that are introduced by that discontinuity are so high, they're not even close to what I'm measuring. So no windows for me, and that's it. That's the setup. And then this thing, once it's set up, because I have it on auto, it's going to automatically track. Even if I changed the frequency on there or I adjust the amplitude, it'll automatically continue to track the fundamental and give me an accurate THD. So as you can see, we have a good clean waveform. We have 1.3%. I'll lower it a little bit. Okay, nice and low. We have 0.8%. Now let me take it up near clipping. Okay, back it down right before clipping. We have 1.4%. Let me go into clipping. A second. Hold on. I needed to take another reset the distortion measurement there. I tinkered with the setup. So, okay, so let me start over again. We have a nice clean waveform. We're at 0.45%, and if I go down in amplitude, we're still about the same, 0.5. Remember, in a certain range, as you go down in amplitude, harmonic distortion actually increases because it becomes a greater percentage of the signal, the distortion itself. Now I'm going to go up in amplitude right to clipping, and in that clipping we're now at 5.96%. Let me clip it more. We're now at 13%. Now let me back it down right before clipping, 0.4%. We get it right where you start to see it. I'm starting to see it right there, 1.5%. So it tracks nicely. What happened before when I had to reset the thing? I went through the menu, and it's always good when you go through the menu and you get you get everything set up. Although I have those settings saved on here, so it's going to come up that way. Then when you're ready to take, when you're ready to set up, you're ready to take a measurement, just hit Shift THD, and you got it. You don't have to go through that setup menu every time. 1.6, bring it down a little bit to a nice clean sine wave. 0.4. So I can tell you this scope, this is a new scope that I just got, and I wasn't with my previous, in probably my last video I had my old scope. The FFT on there was suspect. It wasn't working right. It was very inaccurate, and the resolution was terrible, and I wasn't able to take the measurements that you saw me take today off of that scope. That's why I bought a new one. I've been needing one for a while, and that was an old, my previous one was an old Chinese knockoff of Tektronix, I think, and the owner's manual was terrible, and the story goes on. I'm happy with the tech. This scope is a, as I mentioned, I think I mentioned it, TRS 1052B. It's about a $500 scope. You can get it more or less here and there, and it is great. Everything I've done with it so far is tip-top, and you can view everything. It's kind of a small screen. I forget the dimensions of it, but still, everything is clear, easy to read, easy to see. It's got a lot of features I haven't even delved into yet. Most of them I don't really need for my purposes. And so with this scope and that THD meter, no problem. I can do about everything I need audio-wise to test, build, repair, whatever I want to do with audio equipment. So I'm going to let this be the final video of my THD, my series on THD. I'm ready to actually get back to doing what I enjoy most, and that's work on, fix, repair, restore, and listen to vintage, classic audio equipment. And just as an FYI, the last thing I'll do is I'll show you, because I haven't come back to this yet, but I've started a series of videos on my Fisher gear, and I've got everything working, and I probably haven't, I don't know where I left off. So this is my listening room. It's in the basement. Right now the speakers I have running are the Bose 901s up there, and here's the Fisher stuff. Got the amp working again. Generations1023.com. Okay, and there's the cassette deck. I think I have a Guns N' Roses thing in there. No, I don't have it. Medicare. I don't have, you know what, I don't have the cassette deck hooked up. Pardon me? Behind. I don't have the wires hooked up yet, but it works. And I'm still got to work on that. That's my favorite amp of all time, my Harman Kardon PA 2000. I'll have to make a video about that one day. I love that amp. There's a whole story behind that one. It's a fantastic amp. One of the best amps ever. in my humble. And so I need to come back to that. I need to come back to making, finishing my videos about the Fisher gear, which I love the looks of that. And then get out my better microphone and do some cranking of the bows up there. Give everybody a listen to that. I've got my racks set up left and right. I've got a lot of audio gear in boxes and stored away, and I kind of want to get them out on display and have them out here. So that's it. Still working on my listening room here. All right. So I've still got a bunch of projects. This stuff. I don't even know what I want to do with this. I want to get my turntable hooked up. You know, also I noticed in some boxes over here, and I forgot about this. My brother-in-law gave me a Harmonic receiver. Oh, that's the PA 2000 box, but for the amp. But inside here is a Harmonic AVR 146 receiver, and it's a beast. And I'm going to have to, look at, I don't know if you can see it. It's a big boy. And it probably has a really good Harmonic they're defunct right now, I think. I mean, they're nothing now, but that was one of the last receiver lines they came out with before they just tanked. I don't know what Harman International did to them, if they sold the name, or I don't know what they make now, but they're just a shell of the company they used to be. But that receiver was still made when they had some integrity, so I'm looking forward to getting that one out and toying around with it and see how it sounds. And it's an audio-video receiver too. It's got all kinds of stuff on it. Okay, well, thanks for watching. I hope somebody found this video interesting in some way. That's why I make them. I don't like showing myself on camera. I don't mind talking into it, but I'm not. I don't like setting a video up and doing a selfie, so I apologize for that if it offends anybody. But this is the kind of stuff I usually do when it's kind of a hobby, and I do it alone, and occasionally I film it, and I hope that somebody enjoys it and gets something out of it. Thanks for watching. Till next time, ciao.